So this is where we actually get to use that table and draw Lewis dot structures, and then finally figure out how many electron domains there are, how many of those electron domains are lone pairs versus bonds, and then predict the shape. So we're going to be using this table, and we're going to be working through these 8 molecules. Okay, so we're going to go through the patterns of drawing Lewis dot structures. So the first step is always counting the total number of valence electrons. Hydrogen has 1, carbon has 4, nitrogen has 5, so a total of 10 electrons. Then I pick the central atom. Of course, we said it's carbon if carbon is in it. I used 4 electrons. That gives me 6 electrons left over. I put them on the outside atoms, but hydrogen doesn't need any more electrons because it is fully stable with just 1 bond. So I minus 6 electrons. I'm out of electrons. Carbon doesn't have a full octet. So this is the exact scenario where I reassign non-bonding pairs, lone pairs. I take those 2 electrons, instead of them just orbiting nitrogen, now they're going to orbit both carbon and nitrogen. So I make that into a triple bond. I've still only used 10 electrons, right? If I count the number of bonds, it's a triple, so 3 bonds plus the single, so 4 bonds. Each bond is 2 electrons. And then the lone pair, that's 10 electrons. So then I look at the central atom here. Around the central atom, if I look like north, east, southwest, how many of those places are there electrons? Just 2. Remember, a triple bond counts just the same as a single bond, because a triple bond there are electrons, a single bond there are electrons. They try to get as far apart from each other as possible, which we can see from the bond angle is going to be 180 degrees. So this guy has 2 electron domains, 0 of them are lone pairs. And what is the name of that shape? Linear. So that is a linear molecule. The next one, CCl4. We will learn naming at the end of this chapter, but that guy is called carbon tetra chloride. Tetra is the prefix that means 4. Carbon has 4 valence electrons. Each chlorine has 7. 7 times 4 is 28, for a total of 32 electrons. Carbon is in the middle. The 4 chlorine come off of it. I made 4 bonds. I used 8 electrons. That gives me 24 left. And 6 around each of the outside atoms takes care of the rest of those electrons. I have none left, and every atom has a full octet. It's stable. So 4 electron domains, 0 of them are lone pairs. That's tetrahedral. And you may not have known that prefix before, that tetra means 4. We often think of quad meaning 4. I think it's the difference between Latin and Greek, but I'm not actually 100% sure. Okay, SF6, total number of valence electrons. Sulfur is 6. Fluorine is 7. 7 times 6 is 42. 6 plus 42 is 48 electrons. This is going to be an expanded octet because sulfur is in the center. Draw 6 fluorine around it. 6 bonds. Each bond is 2 electrons. So I just used 12 electrons, which gives me 36 electrons left over. That is going to, those electrons will be used up by the 6 electrons I need to put around each fluorine. So I've just used up all my electrons. Everyone is stable. Remember, sulfur can have an expanded octet because it has electrons in the 3rd energy level or higher. So then I look, 6 electron domains on that table is called octahedral. Oh, there's 0 lone pairs. So it's octahedral. I know students find that infuriating because they want it to be something that has to do with 6, or octahedral has something to do with 8. We talked about that on the other one, that in 3D, you'll see when we look at the models of this, this has 6, although it has 6 bonds coming off of the central atom, it will have 8 sort of faces, 8 sides. And the last one on this is H2S. Hydrogen has 1. 1 times 2 is 2. Plus sulfur 6 is 8 valence electrons. Sulfur is in the middle. I made 4 bonds. Excuse me, I made 2 bonds. I used 4 electrons, so I have 4 left over. I don't need to put them on the hydrogen. I put them on the sulfur. 1, 2, 3, 4. Everyone's stable. My Lewis dot structure is done. And now I look northeast, southwest around the sulfur atom. How many electron domains? Remember, a lone pair counts as 1 and a bond counts as 1. So this guy has 4 electron domains. So if you look on the table, 4 electron domains could be tetrahedral if all 4 are bonds. It could be trigonal pyramidal if there's 1 lone pair. And since there are 2 lone pairs, the name of the shape is bent. In reality, and you have seen this mostly with water, this is a more accurate way of representing the 3-dimensional shape of that hydrogen sulfide molecule. Hydrogen, dihydrogen monosulfide molecule. The next, so now we have 4 here. And these 4, what I would say is, we've done 4 of them. Pause the video, do these 4, and then unpause the video and see how you do. See if you got them correct. If you don't get the Lewis dot structure right, go back and make sure you are following those steps. So pause the video here and then come and check back. Okay, so let's go through these. P, BR, BR. Okay, I'm gonna skip ahead and just give you the answers to the 4, and then I will go through and actually do them out. This guy is 5 electron domains, no lone pairs. So he is trigonal bipyramidal. ICl4 has 6 electron domains and 2 lone pairs. So he is square planar. Water is bent. It has the exact same structure as that H2S. And ClF4 is T-shaped. So if you got those all set, you're done. If you got any of those wrong, I'm going to go through and actually, do them out like I did the previous 4. So PBr5 would be 5 plus 7 times 5 is 35 for a total of 40 electrons. Phosphorus in the center, the bromine are around it. I made 5 bonds. Each bond is 2 electrons, so I used 10 electrons. That gives me 30 left over, and that's going to be just enough to put 6 electrons around the 5 non-central atoms, the 5 outside atoms. So now I am done. How many electron domains around the central atom? It's only bonds, so 5 electron domains, 0 lone pairs. That's trigonal bipyramidal. Think of 5 tri bi. 3 plus 2 equals 5. That's how you can remember trigonal bipyramidal is 5 electron domains. ICl4 minus. So this is a polyatomic ion that we have not talked about yet, but it has iodine has 7. Chlorine has 7 times 4 is 28. And remember, the negative sign means it has an extra electron. So we add 1 more electron for a total number of electrons of 36. Iodine in the middle, the 4 chlorine are around it. I just used 4 bonds, 8 electrons. That gives me 28 left over. 1, 2, 3, 4, 5, 6. We always put on the outside first. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 4 electrons left over. Where do I put those 4 electrons? On the central atom. And we just kind of squeeze them in there. And then I go look on the table. 6 electron domains, right? 4 bonds, 2 lone pairs. So that means that I'm in that very last one, the octahedral group. If it has all bonds, it's octahedral. If it has one lone pair, it is square pyramidal. And when it has two lone pairs, those lone pairs go on opposite sides. So this is called square planar. All those chlorine and iodine, this is like a flat molecule. And one lone pair is on the top and one lone pair is on the bottom. Water. So 2 + 6 is 8 valence electrons. Oxygen in the middle. To the 2 hydrogen, 2 bonds, 4 electrons, gives me 4 left over. Hydrogen don't need any extra electrons, so I put them on the central atom. It has 4 electron domains. Bonds and lone pairs count as electron domains just the same. But two of them are lone pairs. So what is that scenario? That's bent. Okay, water being bent is super important because if you just look at this molecule, you may not realize that it's very polar. So that's the next thing that we do, is talk about whether molecules are polar or not. And finally, we have ClF3. Chlorine has 7. Fluorine has 7 times 3 is 21 for a total of 28 valence electrons. Chlorine in the middle. Remember we said halogens are rarely in the middle, but I actually have 2 examples on this page with halogens in the middle because it doesn't happen, but when it happens, it's often with expanded octets. So the 3 fluorine going around it. I used 6 electrons, so I have 22 left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 4 left. They go on the central atom. We always put leftover electrons on the central atom. So how many electron domains does this central atom have? The 3 bonds, the 2 lone pairs, it has 5 electron domains. But it has 2 lone pairs. So what is the name of this shape? It's called T-shaped. You can kind of see, sort of looks like a T. I'll turn it around that way. It's called T-shaped. Okay, we're gonna have more of these to try in the homework. So give those, if you got some of these wrong, you're gonna have another chance to do it. But again, everything in this chapter builds and builds and builds. So if you didn't draw your Lewis dot structures correctly, you're probably not going to be able to predict the shape. And if you don't predict the shape, you're not going to be able to tell whether it's polar or nonpolar. And whether it's polar or nonpolar is going to be able to tell you what intermolecular forces there are. These are all things that are coming attractions.